Hello, welcome. We are going to be talking today about how you can use NumPy and SciPy to improve your Python programs. So first, let me give you some idea of who this talk is aimed at. Clearly, Python is a vast topic and NumPy is a vast topic. So here I will assume that you have seen Python before, or at least you have experience with programming, but that you have not yet used NumPy, or that you have not yet used it extensively. And I'm hoping that even those who have used NumPy before might still learn some useful tricks or techniques out of this talk. So Python, if you used Python before, you probably know that Python has many advantages over traditional compiled languages. In particular, because of its simplicity, it is excellent for prototyping things. If you have an idea which you want to test quickly, you want to just throw some code together, Python is going to be an excellent tool for that. And this is why Python is growing more and more popular among researchers, because they need to test their idea quickly. However, vanilla Python, sort of the default Python, has this drawback that it's not that good for numerically intensive work, particularly if you have explicit loops in your code. By not that good, I mean if your problem size grows large enough, then the runtime of Python may become quite long, and this will slow down your work. So the goal of this seminar is to show you how you can use NumPy and SciPy to hopefully avoid some of these problems. One important caveat that your Python code, even if you use NumPy and SciPy, it's still not going to run as fast as a code written completely in a compiled language would usually. So I'm not going to talk much about how to help with that, but if you want, there's a full-day course at our summer school at the end of May, which will be talking more about this. So today in the talk, I am only staying within the world of Python and NumPy. Let's first thing, how do you deal with arrays of numbers in default, sort of vanilla Python, without anything added to it? Well, an array in default NumPy, in default Python rather, is a list. So here I have a code where let's say I want to add two arrays. So to do this, I construct two lists. So in this case, I initialize an empty list in Python. And then I have an explicit loop where I ranges from 0 to n-1. And for each I append a number to both of the lists. So at this point, I have, after this line, I have two lists of length n. And then I create a new empty list 3. And then I have a for loop with I ranging from 0 to n-1 again. And I append to this new list. So at the end of this, I have a new list of length n, which is basically an array which is made up of adding the two previous arrays. So if I use default Python, this is how I would treat arrays. However, this is not a good way to do it, because a list in Python is a quite powerful construct. It can hold many things. And there's many techniques associated with it, but it's not really tuned for numerical efficiency. So in particular for this code, when I measure how long it takes to get from this line to this line, so here I import the time module and I start timing here and I end timing here. This takes 3.23 seconds. And in what follows, I did all my tests on a Graham cluster node, so that's for consistency. So that's where the numbers are coming from. So this number right now doesn't tell you much, but we'll see how it compares with other techniques. So notice that here I am creating this list as I go over the loop. So you might wonder, well, maybe the list, the memory allocation is taking up some of this time. So just to verify that this is not really the case, I do the same thing, except in this example, I allocate my whole list before I start timing. So here I have list 1, list 2, and I make a list 3 here consisting of just zeros, and then I start timing. And then inside my loop, I take the ith element of the first list and the second list, and I add it to the ith element of the third list. And notice that this takes roughly the same amount of time. It's actually a little bit faster, just a tiny bit. However, remember that in practice, these measurements, they are somewhat variable. So they are meant to be only ballpark in this case. I wasn't really that rigorous about timing this. I mean, you would really have to do longer runs to get more quantitatively accurate timing. But the basic point is that the allocation wasn't the problem, because even if we allocated the list before and start timing later, we still get roughly the same amount of time to run this code. Okay, we can, even within vanilla Python, we can avoid using an explicit loop using a map function. So map function is something relatively simple, so let me illustrate it here. I make myself a list in this example. A list consists of numbers 1, 2, 3, 4, 5. Then I define a square function. So this function takes x and returns x squared. And what I can do with map is I can call the function map. And then the first argument is the function I want to apply. And then the second argument is a list. And what map will do is it will take each element in the list, apply a function to it, and make a new list. And actually, I have to explicitly include a list function here to make sure that I get a list out of it for some technical reasons. Actually, in Python 3, a map will not return a list by itself. You have to add the list function to ensure that this happens. But as you can see, I have a function which I'm applying to each element on this list, and I get a new list. And sure enough, because the function squares the elements of the original list, I get 1, 4, 9, 16, 25. I could also have a function of two variables, and this will just add two lists. So in this case, I define an add function, which takes arguments x, y, and returns x plus y. And then I call map with more arguments. So I have the add function, and then items again. So I supply the same list twice. So you can clearly see that the resulting list is 1 plus 1, 2 plus 2, 4, 3 plus 3, 6, and so on. So this is the map function in Python. Okay, so now let's look at the same operation we did before, but right now we will be able to avoid a loop when we are adding the two arrays. So I still make my arrays using lists, and I start timing. But here I don't use an explicit loop. Instead, just as we have seen in the previous example, I use map and list. So this creates my new array. And I time this, and it takes 1.26 seconds. Actually, already this is 3 times faster than an explicit loop, even within vanilla Python without any add-ons. So, that's of benefit. And you could argue that it's a, also cleaner looking code. All right. So how would we address this problem with NumPy and SciPy? Well, the first question is, what are NumPy and SciPy? These are two very powerful numerical libraries which are not part of default Python. So these are Python modules which you have to install, but they should be relatively easy to install. And what they allow you to do is they contain routines written in highly efficient compiled languages, and they also contain array objects which are highly efficient in storing numerical values compared to the default list in Python. So once you import the NumPy and SciPy modules, you can call these routines and make your Python code more efficient and faster. So how do you get to NumPy and SciPy? Well, if you are using a Compute Canada cluster like Graham or Cedar, you can load a Python SciPy module. We call it Python 27 SciPy stack. So if you're using Python 2, you do module load this. If you're using Python 3, you do module load that. Now, if you're using your own laptop at home, a convenient way to install Python with NumPy and SciPy enabled is using Anaconda. And you can download it from this web address. So a very quick overview of NumPy. I apologize for the brevity, but I will also be discussing NumPy usage in the code examples I will show you later on. So to make NumPy visible to you inside Python, you run import NumPy. In many code examples, just as a shorthand, you will see import NumPy as NP, and then all the routines are np dot instead of numpy dot. I've chosen just to use numpy, but you can use either one as you prefer. So after I import numpy, first I want to make an array. So one way to make an array is from a Python list. So here I have a list of numbers. I provide this as an argument to numpy.array, and this will create a new array A containing, as you would expect, 0, 1, 2, 3, 4, 5. And this new array is a numpy array. I can accomplish the same thing using numpy.arange, which is a special array creation function which will generate array members 0, 1, 2, 3, 4, up to 5, but not including 6. I get the same array. And clearly this is useful because if you are using a short list to initialize an array, you're fine, but if your list is very large, you really want to generate it automatically. So once I generate this numpy array A, I can query its data type, and sure enough, it's numpy.ndArray. What can I do with this array? Well, I can still treat it just like I would a list in Python. So in particular, if I want to access a specific member, let's say I want to access a member at index 3, I can do a brackets, square brackets 3, and this returns that member. I can also add these arrays, and the addition is element-wise. So if I define a new array made up of A plus A, what this does is it takes each element of A and adds it to the corresponding element of A, and you get a new array. So we have 0 plus 0 is 0, 1 plus 1 is 2, and so forth. If I do A times A, I get element-wise multiplication of A as a result. So I have 0 times 0, which is 0, 1 times 1, which is 1, 2 times 2, which is 4, and so on. So all the operations on arrays are element-wise. And finally, if I define a function, let's say in this case I define a function which squares x, I can apply that function to the whole array, and again the evaluation is performed element-wise. So which is sort of like map, which we have just seen in vanilla Python. So, f of 0 is 0, f of 1 is 1, f of 2 is 2 squared, which is 4, and so on. So this A times A is equivalent to f of A. All right. There's one very important point. So there's many benefits of Python, but one drawback is that you have to worry a little bit more about precision, in particular integer precision. So your default Python has basically infinite precision for integers. So your integers can have as many digits as you like. Of course, in practice, you are limited by the memory of your computer, but if you don't exceed this, you can have arbitrarily large numbers. And the way Python implements this is, after a certain limit, integers are stored as type int, but once you make your integer large enough, it becomes type long. So int is 32-bit. Once you exceed this, you get to type long, and this in practice is infinitely long. Now this is, if you have a problem which truly deals with very, very large integers, it's actually useful. But in most cases, your integers are smaller, and you don't want the overhead of storing an infinitely long integer, which basically is what Python has to deal with. So basically, you'll be fine using NumPy as long as your integers are not unreasonably long. So something important to remember. All right, so let's use NumPy now to add our two lists. So I am doing the same two things as in the previous cases. But first, I want to show you what not to do, the bad way to proceed. So I'm going to define my original list, and so I have list 1 and list 2, and I want to add them to make a list 3. So I fill list 1 and list 2 with numbers 0, 1, 2, up until n-1. So using numpy.arange, as we've seen before. And here I specify that I want to store these numbers as 64-bit integers. So I do that. And I also define a new list to store the result, which I'll make empty. So for now, it's been allocated in memory, but it's empty. And now I do an explicit loop with I ranging from 0 to n-1, and I add the lists element by element, and I time that from here to here. And you can see that it takes 5.18 seconds to do this. So the first thing to notice is it actually takes longer than with an explicit loop in vanilla Python. So this is a very important thing to realize, that just because you're using NumPy doesn't mean that you can get away with using explicit loops. In fact, just the opposite. It seems that explicit loops do even worse. So the proper way to do this is, as we have seen, we want to add two arrays directly. So we define NumPy list 1 and NumPy list 2, and then I start timing, and then I generate a new list just by adding NumPy list 1 plus NumPy list 2. So I'm adding two arrays directly without loops. And this takes only 0.04 seconds. So this is the right way to do it. So let's put all these timings on a single slide, so just so you can see what's going on. So if I'm using just the vanilla Python, storing my numbers in a Python list, that addition took 3.13 seconds. If I'm using a map without an explicit loop, I improve this to 1.26 seconds. If I switch to using NumPy, even though NumPy is meant to be efficient for numbers, when I do an explicit loop over a NumPy array, it's actually slower than vanilla Python. It's 5.18 seconds. But when I do things properly, avoiding a loop and just adding the arrays together in a direct operation, it only takes 0.0406 seconds. So if I divide this by this, I can see that NumPy with an explicit loop is about 100 times slower than NumPy without it. So you can clearly see how important it is to avoid explicit loops in Python if you're doing something numerically intensive. And the way this will matter is, if you're writing a quick prototype code, which takes only a fraction of a second to run, then it probably doesn't much matter whether you use an explicit loop or not. But the moment your program takes any significant time, you will start noticing this 100 times factor of 100 times slowdown, right? Clearly, there's a difference between a code which takes 1 second to run and a code which takes 100 seconds to run, and so on. So, as you can see from this, it's really good to get into the habit of just avoiding explicit loops a priori in Python if your code has doing any kind of a large amount of work over numbers. Okay, so we should definitely use NumPy. We can see we should use NumPy arrays, and we should avoid loops. So this requires a little bit of a new way of thinking, especially if you are coming from traditional programming languages or default Python. If your background is in programming C or Fortran, you're just very used to solving problems with loops, right? So it might be a little bit hard to step away from this approach and do it without loops. You really need to learn to basically take traditional loops and managing to do without them. So how do you do this? In particular, the easy loops, just adding two arrays, which I have shown you so far, they are easy to replace. But what if your loop contains an if statement, for example? Or what if there is a reduction? What if you are looping over some variable and accumulating data? So let me show you how to get around those problems. So let's say we have an array of numbers, and we want to count the number of members in this array which satisfy some kind of a condition. So in my particular case, I will make myself an array of random numbers. So in NumPy, there's a .random function which will conveniently do this for me. So here I will have an array x, which by default contains a bunch of floating point numbers between 0 and 1. They are distributed between 0 and 1. And I want to count how many of them are below a certain limit. So in this case, how many of them are below 0.2. So in practice, how many of them lie between 0 and 0.2. This line here, just for clarity, I'm seeding the random number generator. This is useful for testing. It just ensures that you get the same sequence of random numbers every time, which is great for debugging. But of course, in real life, you probably want to have a different seed for each run. So you should either remove this line completely or generate the seed somehow. Okay, so here I have an array of numbers. quite large, about 10 million numbers in it. And I want to see how many numbers are below 0.2. So if I do this with an explicit loop, I can loop over I ranging from 0 to n-1. And then for each element in x, I test, is that element less than the limit? And if it is, I increment this number by 1. So here I initialize it to 0, and then I basically count how many elements of x are below the limit. I start timing here, I end timing here. And this takes 2.804 seconds with an explicit loop. How do I do this without a loop? Well, it turns out that I can generate an array of booleans from imposing some kind of a condition on an array. So here is my array x, which consists of a bunch of numbers between 0 and 1. Now this x less than limit, this will in practice generate a new NumPy array which consists of just true and false values of the same length as x. And basically, for each element in x, if that element is less than limit, then I get true. And if it's greater than the limit, then I get false. So xbool, this array, is just a bunch of true and false values. Now what NumPy does is, if I now take x and s argument in square bracket, I provide this Boolean array, I get a new array which consists only of the values of x, for which xbool has a true value. So basically I'm applying a filter here. So xFiltered will contain only those elements of x which satisfy this condition. So once I have this new array, well, I just have to see how many elements are in this array. So I can use a standard Python function called len, which applied to an array gives me the number of elements in that array. So I do this here, and I can print this value which contains my answer. So if I start timing here before generating the filter, and I end timing here after applying the filter and checking the length of the array, this whole thing took 0.7 seconds. So this was 38 times faster than using an explicit loop, which is a significant speedup. So you can see that by using this methodology in NumPy, where you can generate an array of booleans from a condition applied to an array, and then use this array of booleans to filter the original array, and then determining its length, I can do my reduction without using an explicit loop. Okay, let's consider a variation of this. Let's say that instead of counting the how many members of x satisfy a condition, I want to set all the members of x which satisfy a condition to 0. So if I have an explicit loop, I do a loop from I to n-1, and then for each element of x, if x of I is below the limit, I set that element to be 0. So I do this, and it takes 2.941 seconds. How do I do this without a loop? So how do I eliminate this loop? What I can do now is I can again use the Boolean array. So the interesting thing about the Boolean array is if a value true, if you multiply true times a number, it's equivalent to 1 times that number. And if you multiply, and false is equivalent to 0. So x less than limit will be a Boolean array of true and false, except I want to set the elements for which this is true to 0. So I want to apply a minus sign to basically flip that array. So if I do minus of a Boolean array, then all the true elements become false and all the false elements become true. So all the zeros become ones and all the ones become zeros. So this array minus x less than limit will basically generate zeros for all the situations where this condition is true, and 1 when it's not. And if I multiply the elements by 1, nothing changes, which is what I want. And if I multiply them by 0, negative 0. So in the end, I have a new array X, which applies this filter to the original X. And there we go. So I accomplished my task without using a loop. And this took 0.05 seconds, which was 55 times faster than using an explicit loop. So again, same thing, just without using an explicit loop, I get a factor 50 speed up. And finally, what if I want to do something more complicated? What if, for example, I want to apply 2 conditions? So what if I want to set all the members of X which are less than 0.2 to 0, and then I want to set all the members of X which are greater than 0.8 to 0 as well. So I could do what I did before twice. So I could apply the first filter to X, and then apply the second filter. Now the question is, could I do this in one line? So if you think about it, what if I try to combine this condition and this condition with an OR? So I could have X equal to minus and then X less than lower limit, or X greater than upper limit. Now this is a valid construction in your typical Python, but it won't work in NumPy. You'll get an error if you try to do this. So in practice, what you need to do is to combine these 2 Boolean arrays into a new array using some kind of a logical operation. You actually have to use a NumPy logical operation, in this case, NumPy logical OR. So this takes this Boolean array, and makes a new one, which I call mask. And then I can apply the mask Boolean array to the negative of, so the opposite of the mask array times X will generate what I need. All right, so now let's move to SciPy. So NumPy is a set of routines for your basic operations over numerical arrays in Python, and it's already very useful such as this. But then SciPy is something on top of this. So SciPy is a vast library of powerful algorithms from all areas of mathematics, science, and engineering. It's truly a vast collection at this point, and if you want to explore it, you can go follow this reference. And so what SciPy should allow you to do is quickly employ very powerful algorithms in your Python code. So this will save you a lot of time, this will make your code faster, and it allows you to very quickly incorporate very powerful algorithm in the code you write. And as far as I know, this is one of the reasons where Python is so popular, because in other programming languages, it's still possible to import other algorithms, but usually it just takes more work on your part to make that happen. So I wanted to pick one example to illustrate how this works, and somewhat arbitrarily, I picked the example where you search for nearest neighbors of a point in a set. So for simplicity, let's think of 2 dimensions. Let's consider a bunch of points in 2D in a set A. So point x0, y0, x1, y1, and so on. And now we are going to pick a new point, xt, yt, and we want to find the point in A which is closest to it. So, you know, the sort of brute force way to solve this is we could loop over all the points in A, compute the distance between each point and our new test point, and then look for minimum distance. So that's what I'm going to do. And just to illustrate how the bad way is actually quite slow, I will use an explicit loop again. So what do I do here? I'm working in 2 dimensions, so I generate 2 arrays of random numbers between 0 and 1. So in this case, I have xx, which will contain the x coordinates of the points, and yy, which will contain the y coordinates. And now I want to join them to create a new 2-dimensional NumPy array. So I haven't talked about that yet, but NumPy can store arrays of arbitrary dimension. And I have to use this dstack function, which is a way in NumPy to join two arrays. I have to take, again, this is just the artifact of how this function works. I have to take the 0th element of the result. But once I do this, I have an array of length n consisting of pairs of points. And then I pick a test point. So in this case, I make a NumPy array with only one point containing the test point. So now I will have a loop where I will go over all the elements in the joined array, and I will calculate the distance from the test point. So here I take joined array, the ith coordinate, the ith point, the first coordinate, and then the second coordinate. Then for each coordinate, I subtract the coordinates of the test point. And I square this. I take the square root using the NumPy SQRT function, and I check whether this is less than the current minimum. And if it is, I update the current minimum to a new value, and I set the index where this minimum is occurring. Notice here that I have to initialize the min, and NumPy provides a convenient numpy.infinity, which you can initialize with. So I have a loop, and after I traverse through the loop, I will indeed find the point in the joint array which is closest to this one. And when I do this on the gram cluster, it takes 27.5 seconds. Okay, now without an explicit loop. So my code starts off as before, but instead of doing a loop, I now compute an array which holds the distances for the distance for each point in the set from the test point. So the way I do this is now I have to do a little bit of slicing. I haven't mentioned this before, but basically the joint array is n by 2. So I want to take all the values of n, which is what this column indicates, and then so I take all the x coordinate values of n. I subtract that from the point coordinate of the test point, square this, and here all the values of n, and subtract the other coordinate. So again, we are doing this element by element. So we take the 0th element of joint, its x coordinate, subtract the point. We take the 0th element of joint y coordinate, subtract the corresponding y coordinate, and we store the result in the 0th element of d after we take the square root, and so on. So at the end of this, I have a new array which contains just the distances. And now I need to find the minimum of this. So NumPy has a special function called amin, array minimum, which will take your array and return the minimum, which is what I need. And there's also a function called argmin, which will tell me where this minimum occurs, at which index. So I call that, and I get imin. Okay, so I time this, and I start timing here, and I end timing here. And this took only 0.566 seconds. So it's 48 times faster than the explicit loop. And so the question is, so we clearly see how, again, explicit loops are bad, and we should definitely avoid using them. But could we do even better than this? We can by using an algorithm, which we will get from SciPy. So what I did here was basically a brute force search. I had a bunch of points in a set. I had a test point. And to find the closest point, I would check every single point in my original set and find the minimum. So this scales as n, where n is the number of points, because I have to check every single point. So is there a faster way to do it? Well, if I could organize my data in the original set in a way which makes searching more efficient, then I could search for this point faster. So I basically can split my work into two parts. First, I can organize my points, and this will not be quick. It takes some time to organize my points into some scheme, but once the scheme is complete, my search should be fast. And the way to organize your points in multiple dimensions is using the Kd3 algorithm. So here it is illustrated in 2 dimensions, but you can use it in any number of dimensions. So basically, you pick some starting point. Here it is A. And then you construct a tree where basically all the points, so here we use x as a dividing axis, and then all the points to the left will be to the left in this tree, to the left of A, and all the points to the right of A will be in this part of the tree. And then we pick some other points, and now we split along the y-axis, and then for B, all the points to the upward of the y-axis will be to the left, and all the points downward will be to the right, and so on for f of g. So this is the basic idea, and you construct this binary tree for your points. And once this tree is constructed, there are techniques which, given some arbitrary point in this space, once you have the tree, you can traverse the tree and find out which of these blue points is closest to your test point. If you want to find out more about this algorithm, how this algorithm works, you can check Wikipedia or other websites which explain it really well with nice animated graphics. But this is just to give you the basic idea. So how is Kd3 implemented in SciPy? Well, here I'm just giving you screenshots of the help function in SciPy itself. So the Kd3 is part of the spatial directory of modules. So here I do from SciPy import spatial. And then immediately within Python, I can find help information about this function. So Kd3 is a class in SciPy spatial. So I call help on it, make it extensive documentation. So I can see it's a class. It's Kd3 for a quick nearest neighbor lookup. And skipping ahead a little bit, I can see that this class takes data as argument, and data is an array of points in dimension m. And there's other optional arguments, which I don't have to give. All I need to provide is the data, which is a NumPy array. And then what are the methods for this class? There's many, but one particular method is query, which allows me to supply a point or multiple points, x, and then find the nearest neighbor of this point x. And once I call this method of this class, it will return an array of floats, which will be the distance to the nearest neighbor, and then an array of integers. So for each point, it gives me the distance to the closest point and which point is the closest. All right, so let's now solve our problem using Kd3. So now I have to import the spatial methods from SciPy. I generate my random x and y arrays as before. I join them using dstack. So everything is the same here. And now I construct my tree. And this is very simple. I just call the spatial.ckd3 class. I initialize it with my data. I provide this as the initialization argument, and I get a new object called tree. And I time how long it takes to construct the tree. And this is not a trivial task because you do have to range over all the points in joint to construct the tree. It takes 12.9 seconds. However, once I have the tree, I now define my array of points, in this case just one point, and I call tree.query. So I call the query function supplying the points argument. And this gives me A and B, where A will be the distance between this point and the closest point to it in joint, and then B will be the index within joint of that point. So basically A and B are the solution I'm looking for here. So now I time the query, and I can see that this is blazingly fast. So yes, it takes time to construct the tree, but once the tree is constructed, it's blazingly fast to find that point. So let's look at the timings now to make very clear what's happening. If I use an explicit loop, it takes 27.5 seconds. If I use NumPy array operations, it takes 0.566 seconds. So it's about a factor 50 speed up. So even doing this is clearly very important. You really want this factor of 50 speed up. So you want to use an explicit loop. But what if we use the Kd3? Well, if I include the tree construction, it takes 12.9 seconds. So that seems discouraging, right? Because, well, it's actually slower than using the arrays. If I don't include the tree construction, it takes a very short amount of time. So all of these results are just for one test point. So you can see that if you have only one test point, this is the best method. Just use explicit array operations. But in real life, you will have multiple test points, typically. You're not just testing for one. You're likely to have many. And it is for this case that the Kd3 method tends to become superior. Because remember that the tree has to be constructed only once. You construct the tree just once at the beginning, and then you can use it to query points. So in particular, if you have a large number of points, then the cost of constructing this tree will start to grow ever less significant as you are increasing the number of test points. And in the limit of many test points, only this number matters, because you just do this once and then you apply this operation multiple times. So if you are in this limit, you will actually be a factor of 1,000 times faster over using the standard array approach. So if I take this divided by this, I get a number which is close to a factor of 1,000. So clearly, if you are writing a program which has to query many points, you want to use this technique. So you want to leverage the power of SciPy. And keep in mind how simple this was. So yes, we had to read the documentation. We had to figure out where to find the documentation. But in the end, we are using this very powerful algorithm just using 2 lines, right? We are constructing the tree, just 1 line of code, and we are using the tree in just 1 line of code. And here we are looking for the closest point to a set of points, but there's many other functions for the tree class which you can use to provide you other useful geometric information. All right, so to summarize, I hope I have demonstrated to you that using NumPy to access numerically efficient array routines is very important in Python, giving you very useful speedups. But you have to keep in mind that even with NumPy, you must avoid explicit loops. So NumPy by itself is not a cure for using explicit loops. And even if your code uses NumPy and avoids explicit loops, you can gain additional speedups by taking advantage of very powerful algorithms which SciPy provides.